All right, getting into the last lesson here in chapter 12 on vectors. We're now looking at the real life application of vectors. And so one thing I want you to come back to and remember that we mentioned in an earlier video is the relationship between the equation of a vector and just the regular equation of a line that you've dealt with in the past when you did like a y equals mx plus b format for the equation of a line, right? Where if you said mx plus b, where b was the beginning of your line, or usually the y-intercept, but it was a point on your line, and the m, the slope, was the direction that you traveled from here. And so that's the exact same idea with the equation of the vector, is we have a point on the line, and then this, the directional vector, is where we go from there. And so in the drawing that you see over there on the right, we have a position or a point on the line at 2, 5. And then from there, this is where we would travel. We're going right 4 and up 3. And so if you see at the initial point at time 0, or if t was 0, this is our starting point. This is the initial point at 2, 5. And then based on the horizontal, this tells me to go positive 4 to the right. This tells me to go positive 3 up. So from here, if I go right 4 and up 3 one time, that's my new position after t is 1, or after 1 second, or 1 unit of time, whatever that represents. If I had another unit of time, then again I would go right 4 and up 3, and that would be my new position after another unit of time. So keep that in mind, that this is all this represents, is just that basic y equals mx plus b concept, where this is a position or a point, and then this is where you move from there per unit of time. And that's a big concept, that per unit of time. That way we can then make t equal our units of time. And so you'll see that come up down here in number 1, where we deal with making sure that this is in units per time. And so we look right here, so the initial position of that equation was at 2, 5, and that was where time is 0. So that's the initial position, or the position vector. The velocity vector is the same thing as the directional vector. So when they refer to velocity, they're always referring to the directional vector within the equation of the line, and that is per units of time. Anytime they refer to speed or length or distance, those types of things, those are always the magnitude of your velocity vector. And so that's where we're going to come up with the numbers for that. So looking at a few examples here. So particle moves at a constant velocity along a line, so its initial position when t was 0 was 3, -1. And so here's our position vector at 3, -1. That's our starting point. So you'll see that right here within the equation at 3, -1. And then 2 seconds go by and our new position is at 5, 5. So a couple questions that we have to now find. We know that we started at 3, -1, and if I am now at 5, 5, 2 seconds later, or 2 units of time later, what would our velocity vector had to have been? And that's the same thing as basically saying what was your slope. That's really what the directional vector is, or the velocity vector is. And so if you look at this one here, so for part A, we started here when time was 0, and then 2 seconds later I'm at 5. So just start by looking at the change in the x position. It was at 3, and now it's at 5, 2 seconds later. So from 3 to 5, we went 2 units over 2 seconds period of time. And so as far as units per second, so right here we went from 3 to 5, so we had a total distance of 2, but if we divide that by the amount of time that it took us to get there, this is the value that we're going to get for that velocity vector. Remember, we always want it in per units of time. Like you wouldn't say, I went 100 miles per 2 hours, right? You would break that down and you would say, I traveled 50 miles per hour. And that's the way we always break it down, is per unit of time. And so it's the same thing here, as we're dividing the distance that we traveled over the amount of time that we traveled to get it into a unit vector, like you're seeing it right here. So the same thing with the y value. You started at -1, you went to 5, so that's a total distance of 6 units in the course of 2 seconds. So here we are, we traveled a total of 6 units over the course of 2 seconds. And so if we create a unit vector out of that by just dividing by the amount of time that it took us to do that, we're going to get the value of 3 for that y coordinate, or that y value. Speed is always a magnitude question, so this is the magnitude of your velocity vector. So here's our velocity vector. If we did the magnitude of that, we're going to get the square root of 10, and that's our speed. And then now we can write the equation of that line, the equation of the vector. So we have our initial position right here, and then we throw in our variable of t, and then we have our velocity vector. Moving on to number 2. So now we have a constant velocity along the line. They're giving us a velocity vector right here at negative 12.25 units per second. After 6, we'll just call it seconds, after 6 seconds, or 6 periods of time, this was our new position. So now we're trying to figure out what the initial position was. And again, this is just like a y equals mx plus b value. They're giving us the future amount, like a future y value. We have our x value, and we have our m, or our slope, our velocity vector, and we're solving for the b value. We're solving for the initial position. So again, this is just like that y equals mx plus b format. We're solving for the initial position. So we just do those parametric equations, write one equation for x and one equation for y, and solve it. So going down the line, we're going to have our future position. So negative 49 is equal to x plus 6 times negative 12. And if we clean that up, we get 23 for the x component, and then you can do the same thing for another parametric equation for the y component. For the position after 8 units of time, or after 8 seconds, well, now we have our initial position. We have our velocity vector that was given to us, and now we can sub in any amount of time that we want for t and figure out our new position. So if we sub in the 8 for t, here's the new position that we would have. Moving on to number 3. So again, we got 2 vehicles leaving at 5 o'clock. One velocity has a vector of 26 over 16. That's kilometers per hour. So we're working with hours on this one. And then the other train had the velocity vector for 5, negative 12. And we want to know the distance between the vehicles 2 hours later. So keep in mind that this was in units per hour, and we're traveling over the course of 2 hours. So we don't have an initial position vector for this, but we don't really need one. It's like they're starting at 0, 0. So they're originating from the same train station, from the same place. And so it's just like we're moving from 0, 0. So it'd be the same thing as having a position vector of 0, 0, and then you could say plus t times the velocity vector that we have here. Since this happened over the course of 2 hours, well, that means it did this twice, because this is in kilometers per hour. So for the first train, so it started at the origin, and we'll just say it's heading towards some point A. And so it used the velocity vector of 26 over 16, and it did that twice. So remember, that was per kilometers per hour. So if it did it for 2 hours, this is where the new position would be. And if the other train started at the same origin and went towards some other point, we'll call that point B, then it did its velocity vector for 2 units of time, or 2 hours, and this would be his new position. So as far as just looking at the difference between those 2 positions, right? And so here's the first train that went towards point B. This was the train that went towards point A, and so we can see the difference between them would be these position points right here. And so distance is always a question of magnitude, and so we're taking the magnitude of those 2 different points for where they ended up. And if you kind of link this back to what we've done in the past with the relationship between OA, OB, and AB, you can see maybe a little more clearly where this is coming from. So remember, when we had a vector like AB, we did the terminal minus the initial to get the difference, or the vector that was formed from A to B. And so this is the vector that was formed from A to B. And so we're going to take the magnitude of that, since it's asking for distance, and that's going to give us our distance between the 2 trains. All right, number 4. Again, we're still in some similar ideas here, but now we're dealing with 3 dimensionals. And so we have a position particle A, you can see is starting basically at the origin. And then the position of particle B starting somewhere else with a different velocity vector that we see here. So given that they collide, meaning they do have a point of intersection, find the time of collision. So keep in mind that the equation that we have built here on the right gives us some future position point right here that we call xyz. And it's the same thing for this equation right here. Any value of time is going to land me in a future point of these values right here for xyz. Well, given that these particles do collide, that means at some value of time, they have the same point. They have the same xyz point. And so I can simply set this equation equal to this equation and solve for t. And so that's what you're seeing now broken down over here on the left. We're creating those parametric equations. So again, for the x coordinates, we would say 0 plus 2t. For the y component, we're doing 0 plus negative 1t, and then the z component 0 plus 1t. And so that's all that you're seeing right here in that group. And I know that I can set those equal to the other equation that I see here for the reasons we just gave a minute ago. And if I create those same parametric equations for the second particle, for particle B, again, I'm setting them equal to each other because they have that common point of intersection for x, y, z. And if you look at that, it doesn't matter which one of those equations I choose to use, right? I'm going to get the same t value for all those points. If this were a case where they were asking us to determine if they collide, then we'd have to check all three and see if they all come out to be the same value of time. If they didn't, we would say no, they don't collide. But this particular question, with the way it was worded, says that they do collide, and so I really could have just tested one of those equations to get a value for t. All right, last one down here, we got the lighthouse at origin O. So right here they say initially the ship is at point P, so P is our position vector, and that's the starting point for 40 kilometers to the east of the lighthouse and 20 south of the lighthouse. So if you look at point P, this is where the ship is at right now. That's the initial position from the origin. And so it went 40 east, so positive 40, and then 20 south, so negative 20. And that creates the initial position vector for the ship. And that's what you're seeing right here that we're going to get to in part B. That's the initial position. Then they go on to give us a velocity vector, and they're calling that vector u, but this is the velocity vector, so the negative 8,6. And you're seeing that, again, built into the equation right here in part B. That's the velocity vector for any unit of time. The first part of this, they're just asking us in part A to figure out the vector for OP. So, and that's just kind of that initial position vector that we would have there for point P. Because it's from the lighthouse, and the lighthouse is at the origin, and we went right 40 and down 20, that's why we're coming up with those numbers for the initial position for point P. On part B, this is one of those classic IB show me questions where they basically give you the answer and are asking you to show how to get it. So if we're looking at OT, so now we're looking at this vector right here. So using what we already know, here's a familiar formula for us. So if I'm trying to figure out OT, what are the two vectors that we would put together to create OT? So if I did OP plus PT, right, where this one leaves off, this one begins. And so if I cut out that middleman, I create OT. And so if we plug in the initial position vector and the velocity vector, we get that common equation of the line. And then we just do the parametric equations from there. So 40 plus negative 8t, and then negative 20 plus 6t give us those two parametric equations. And so now right here for the last part, for part C, when is it closest to the lighthouse? And they basically set it up for you. But anything would be the shortest distance when it's perpendicular to that point. And remember what we know about perpendicular lines, their dot product equals 0. And that's where that's coming from. So if we just multiply those two vectors together, just formatting after the setup that was given in the problem up above, we just do the product of the horizontal component plus the product of the vertical component, and we're going to set that whole thing equal to 0. And that's what you're seeing over there on the right. And if we just solve it all the way through, we get our value for t.